Hi everyone, I'm Jun. Recently, one of our works were accepted by MICAD 2021. Today, I'm going to introduce this paper. In the beginning, I will introduce the background a little bit. Multi-source observation observes the same objective from different source domains. For example, scientists may scan their cell with different fluorescent materials. In these slides, we use a cell as an example. The left side is the membrane and the right side is nuclear. By using different fluorescent materials, we can get different image from the one cell. However, overscanning may probably cause the death of the cell. This constraint may prevent scientists from acquiring enough microscopic images. Cross-domain synthesis is a potential solution to augment multi-source observation. Given a source domain A, cross-domain synthesis aims at generating corresponding images of the same objective in a target domain B. However, many existing methods couldn't handle the issue that two domains come from different sources with quite different spatial features. So we propose a new framework to address this issue. Before I introduce our model, I would like to talk about the background of the baselines. GAN is a popular baseline for image generation. Consistent loss helps GAN synthesize cross-domain images without pair training data. However, this technique couldn't handle two objectives with distinct contours. Our model aims to embrace this challenge as well. Next, I will introduce our model architecture. Our model is short for BANIS, pronounced BANIS. In our model, we have three basic components. The first is Pioneer. Pioneer is composed of a generator G and a discriminator D. As the successor consists of an encoder E and shares the generator G with the pioneer. The main difference between the pioneer and the successor is their input. For the pioneer, actually it is a vanilla GAN, and it takes the random uniform prior Z as the input, while to the successor, it takes the original image as the input. So next is the coordinator. It sequentially connects two successors. Here we denote the generated image comes from the pioneer and the reconstructed image comes from the successor. Our training procedure contains two stages. Here we will come back to previous slides. On the warm-up stage, two pioneers are trained with given random uniform priors Z, and then respectively generate images. They help speed up the progress of generation. After the warm-up stage, both two successors and two coordinators join the training to enforce the geometrical relationship between these synthesized images. The successors encode the input image into the latent space, and then reconstruct the new images from the latent space. The coordinators use pixel-wise methods to preserve the geometric relationship between the reconstructed images and the original images. Our model has three types of loss function. Adversarial loss is employed to enforce the generated images are as similar as possible to the original images. Identical loss makes the reconstructed images close to the both generated images and original images. Pair match loss enforce the projection inside each successor to ensure these two domains are spatially matched. Next, we will talk about the experiments. Our experiment used a set of C. elegans microscopic image. We use image J software to split the image and then crop out the embryo to membrane and nuclear. The first row is the membrane, and the second row is the nuclear. We propose an evaluation metric called geometric matching index, which is short for GMI, to evaluate the performance. At first, we reconstruct the images by the successor, and then we extract their binary mask. After that, we compute the dice coefficient between these two masks. After that, we compare the dice with our given threshold. If the dice is smaller than the threshold, we say it is good. The intuition is that the overlapping will be lower if two images are matched. Next, we will present some results between our model and the baseline. The first two lines come from our model, BANIS, and we can see that the synthesized result has cleaning contour for the membrane, which is better than the other two. In the last row, we can see that the autoencoder fails to generate a clear nuclear. Overall, our model outperforms the other two baselines. We also evaluate the performance based on our proposed metrics under different thresholds from 0.1 to 0.3. The result shows that our model still get good performance and even under a very strict threshold. In conclusion, we propose a model BANIS to synthesize geometrically matched images from multiple domains that exist entirely separated spatial patterns. The experiments indicate that BANIS successfully synthesized diversified, geometrically matched microscopic images and outperforms two baseline models. Our code is available in this address. We sincerely thank NIH for supporting our project. Thank you. That's all. Welcome to subscribe my channel if you are interested in my work.